Welcome to Astronomy 103. In this last segment, we will discuss life in the universe. So we return to the question that got us stars in this journey in the first place, and that was the question was, are we alone? Well, we don't know the answer to this question yet, but we could ask it better. For one thing, what do we mean by we? Well, what we generally think about we as humans, intelligent life that's capable of communication. And what do you mean alone? Does alone mean one and only? Or does it mean that we are just merely isolated? There are about 10 to 10 stars in the galaxy, actually 10 to 11 stars in the galaxy, and more than that in terms of galaxies. So the universe is vast. So if we're looking for intelligent life, we need to begin first to think about what ingredients for life that are needed to begin with. To do that, we have to look at how life can develop on the one example we have, which is on planet Earth. Prior to understanding radioactive fossils dating was done by stronger rocks, older rocks lying below younger rocks. A striking observation from the 1830s onward was that as you increase the depth of the rock, the complex the depth of the rock was related to complexity and type of fossil found in it. So in the deepest strikes and oldest rocks, like no fossils are found there, only invertebrate mammary fossils just above it, the more complex marine fossils, including fishes, then life on land, being reptiles and then mammals, and finally humans. Right? So basically, life on Earth goes from simple to more complex to the most complex things, right? Starting from the bottom about 4.5 billion years ago, right? The first life on Earth, as we probably understand it, to develop was probably bacteria or some form of bacteria. By the time it had many of the ingredients to make more complex life, right? DNA, proteins, etc. Basically, once you get the bacteria, you've done most of the hard work of making life. The first life that we find in fossils are prokaryotes, which are precursors to multicellular life, single cell creatures that are found in colonies, right? So these are the first organisms evolved. They arose somewhere about 4.1 billion years ago after the Earth's crust began to solidify. About 3.5 billion years when the Earth was inhabited by bacteria and advanced enough to leave evidence of colonies. Life on Earth is made from DNA and proteins. So at the very basic level, DNA codes the proteins for life. Protein is made from amino acids. So for life, you need DNA plus amino acids. So how do you get these things? Right. So two ways for Earth to acquire amino acids. Right. The first way is that the molecules can form basically under conditions very much like the early Earth. So there have been a number of experiments to show this, basically including experiments by Miller and Urey. In other ways of getting this stuff actually from outer space. So organic molecules, including amino acids, are present in some meteorites. They're probably formed in the interstellar medium, probably on dust grains, right? So here's basically the famous Urey experiment. They basically filled the Miller or Urey experiment. They filled a task full of water, carbon dioxide, nitrogen, and hydrogen. They zapped this thing, basically mimicking lightning. And if they do this, basically after a while, about a day or so, they basically found that you could find some very complicated organic molecules that were formed in this experiment. So here's Stanley Miller in this experiment here. Okay. Now you can also find amino acids on meteorites. Okay, so basically 16 amino acids were found in the Murchison meteorite shown here. So complex organic molecules are also found in interstellar space. So you basically form on Earth, form in space. Second ingredient of life is DNA, which is a molecule that makes copies of itself. So this is basically the key thing for life. Is you have to basically make copies of itself. So this is the important functions of life to reproduce. Not yet clear how the first molecules did it, right? But we know DNA can do it. In any case, the chemical reactions drive life, replication, and energy takes place in the present liquid water. Now, may not be the only way to do it, but the only way we know how. So if we were to look for life, we have to look for places that have liquid water. And that goes true for extrasolar planets as well. So there are possible habitats in the solar system. There's clear evidence for water on Mars, we discussed earlier at early times. No clear evidence for life. Europa may have water below. It may be heated from tides. All right. Titan's lakes of methane and ethane might also allow some sort of self-replicating molecules to exist as well, but it's very, very cold, and so the extreme. But however, there are extreme climates on Earth with life. So, but though they're not nearly as cold as Titan.
NASA tells us today it's
So if you want to look outside the solar system, you want to look for planets that might harbor water, liquid water in plenty.
NASA tells us today it's found a new planet and it is a lot like the Earth. The Kepler Space Telescope spotted it. This is an artist's rendering. Scientists say it's right in the Goldilocks zone. Not too hot, not too cold, maybe about 72 degrees. A good candidate for supporting life. But we won't be going there. It's 600 light years away. Astronomers have also discovered some monster black holes, which are like giant.
So with the discovery of liquid water that might exist in early Mars or Europa and now Kepler-22b and available amino acids, the ingredients for life are seen to be common. So what's the likelihood that life actually develops and how do we detect it? Right? So how do we detect life? Right? So to detect life, we need to understand how life interacts with its environment. So there's a hypothesis known as the Gaia hypothesis, which states that life interacts with its environment to maintain conditions for life. That means life tries to optimize the environment to maintain itself, right? So what Gaia hypothesis is everything is in balance. Whatever waste is made is consumed by other organisms and recycled. The rate of this is kept in balance to maintain conditions optimal for life. So natural geochemical processes are aided by living things to make sure the conditions remain stable for life. Right. So here's one example. This is a carbon cycle. So one example of active equilibrium is the carbon cycle. Plants take sunlight, consume CO2, while animals eat the plants and release CO2. Everything is balanced to maintain the same levels of CO2, roughly speaking. Right. The full carbon cycle is much more complicated. It's not just a balance between plants and animals. Volcanoes also produce CO2. This basically when water weathers on rocks, this basically ends up absorbing CO2. Uh, Weathering on rocks is also aided by plants. Basically, you trap CO2 in rocks by sea life that takes CO2 and makes shells out of it. Right. So here's a full carbon cycle, far more complicated. Okay. So if we know about the Gaia hypothesis, how can we use this to look for life? Because life optimizes the conditions for itself, we can look for plants with lots of oxygen and plants that show signs of photosynthesis. Right? So it turns out that plants on Earth are optimized to absorb sunlight. That's probably not surprising because basically plants use sunlight to basically break up carbon dioxide and basically make sugars out of them. Right? So basically what happens if you look from reflected light on Earth, it has a distinctive red edge, right? Inside of which it basically so this stuff right here gets all absorbed, and then what happens is beyond the red edge, you basically have some reflection, right? So below this, you have very low reflection, maybe a few percent or so. There's the chlorophyll bump at green. That's why plants look green, right? But beyond red, basically, then what happens is that that infrared radiation doesn't really care so much about that. Okay, so if you're looking for the red edge, you might be able to detect signs of photosynthesis. Now, how can you test this idea out? Well, one way of looking is looking at Earth, and one way of looking at back at Earth is looking at the reflection of the Earth on the Moon. That's a real good test of it, right? So the measurements show you that the detection of a red edge, you can detect the red edge for planet Earth at least, right? So there's a red edge right there, right? But it's not yet possible for other planets outside our solar system, right? Now, life may develop elsewhere, but that's not what we really care about. What we care about is intelligent life, and what we really care about is intelligent life that is able to communicate. So what we want to know is what the likelihood that life becomes intelligent, and what's the likelihood that they're able to communicate with us, right? So there's a way to estimate this. It's known as Drake equation. Okay, so it begins like this: you take the number of planets in the galaxies with life, right? The number of planets in our galaxy that have life is the number of stars in the galaxy times the fraction of stars of planets times the fraction of those planets that can support life times the fraction of haploplanets on which life arises. Okay, so let's start out with that guess. The number of stars in our galaxy is 10 to 11 stars, right? Which is roughly about 100 billion or so. The number of stars with planets is actually about 100% now. Pretty much every star has a planet, and many stars have more than one planet, right? So from what we can know from planet hunting, we know this number is actually 100% or so. Okay. Now we ask what fraction of these planets are in the Goldilocks zone. Again, this actually could be close to 100% as well, right? But maybe not. So some planets, some stars may not allow this, but also basically some parts of the galaxy may not allow this as well. So it might be something like a tenth, 100, or 1,000. Let's be conservative. We can basically use about 100 or so. Okay. Now we have to ask, what's the fraction of these habitable planets where life develops? Life seems pretty robust on Earth, so it might be 1 or 1 in 10 or 1 in 100. You could be conservative, say 1 in 10, but actually I'm pretty close. It's probably close to 1. Okay, but I'll just pick 1 in 10 just because I don't want to be too crazy. All right, now we have basically the number of planets that have formed life in the galaxy. So 10 to 11 times 10 to the minus 2 times 10 to 10 to the minus 1, that's 10 to the 8. Okay, so now we have determined that there's roughly about 100 million planets in our galaxy that can support life. All right, so now we want to ask the number of planets in our galaxy with intelligent aliens. Right? We start with the number of planets with life in our galaxy, which you just determined is 10 to the 8 or 100 million. We multiply it by times fraction of life that develops intelligence times fraction of intelligent life that develops technology times the lifetime of technological civilization divided by the age of the galaxy. Okay, so we've determined the number of planets with intelligent life from previously. Now let's ask what fraction of life develops intelligence. Now on Earth, our only example is basically 1. Now this one is really hard to tell because we can't really tell. It could be very small, it could be very large, right? But let's be super conservative, and let's say it's 1 in 1,000, right? We're just gonna be really, really conservative. I think this is a little bit too conservative. Now let's ask basically what's the fraction of intelligence that develops technology on Earth? That was also 1, right? In particular, radio technology. Well, you could argue that maybe it's not that. Maybe you shouldn't look at everything. If you look at the number of civilizations on Earth, there are lots of civilizations that rose and fell on Earth, but only one civilization, namely Western European civilization, ended up developing technology. Of course, this is not really fair because civilizations rise and fall, and over time, basically, at least one of these civilizations would develop technology. So I'm going to basically take also a conservative outlook and take 1 in 10. It's hard to see it basically being smaller than this. All right. Okay, so now, if we do this up to this point, basically we have 10 to the 8 times 10 to the minus 3. So now we have 10,000, 10 to the 4, basically, civilizations or technological civilizations. Now, this last one is the real killer. It's the average lifetime of the technological civilization divided by the age of the galaxy. So we ask, how long have we had technology on Earth? And the answer is we've been communicating with radio for about 100 years or so. Right? So divide by age of galaxy, that's 10 to the 10 years. Okay? So it's times 100 over 10 to the 10. That's 10 to the minus 8. So there should be 10 to the minus 4 civilizations in our galaxy at the present time. Basically, our galaxy should have no civilizations right now at the present time. So this is an interesting number, actually. And the reason why uh, is that we're based on Earth. The real killer, what limits civilizations from talking to one another, is their lifetime, right? That they don't actually live very long. That in order to basically have a chance to communicate with each other, the average technological civilization has to live for 1,000,000 years or so, 10,000 times longer than what we have basically had technology on Earth thus far. And there are lots of ways basically that technological civilizations can kill themselves, right? Back in the day, back in the Cold War, it was thought was basically due to nuclear war. These days, it could be due to environmental degradation. Lots of things can actually end up killing civilizations. And we've had many civilizations in the past, on Earth's past, in human history's past, that have basically come and gone, basically mainly through environmental degradational processes. Right. Now, the problem with this is that over a lifetime of this of the galaxy, there are many civilizations. So by our estimate, there's something about 10,000, right? Could be more, it could be 100,000, right? And so you only need one of these civilizations to figure it out, right? To say, okay, I'm not going to blow myself up. I'm not going to kill my environment, all right? And you have 100,000 chances to not screw it up, right? So you would think if you have 100,000 chances to do anything, eventually you wouldn't screw it up, right? And also, it only takes a few thousand to maybe 1,000,000 years to spread across the galaxy. So fact, basically, once intelligent civilization arises and they're capable of starflight, they should spread around the galaxy like gangbusters. So this is known as the Fermi paradox, that the aliens that are in the galaxy should be here already. Okay, so this is not, there's no solution to Fermi paradox, right? So there's a few possible solutions. So one is that they're already here, basically people who believe in UFOs and stuff. The other possibility is that basically our estimate is wrong. Few civilizations have only ever existed. The third one is that we're the first, and so therefore alone. This I find surprising, right? Because we're very young relative to the galaxy. Intelligent life always deserves itself in eventually. That's one possibility, that all intelligent life just basically blows itself up or destroys the environment. Intelligence eventually destroys others. This is a much more uh, dark outlook, that eventually at some point basically aliens will come and kill us all. Life is destroyed by natural events. This I find very surprising, because if once you're intelligent, you can avoid natural events. The intelligent life may be avoiding us or just don't care. They may be so advanced technologically that they don't even recognize us. It's hard. It might just be that it's very hard to travel between stars, but even with current technology, we can conceive of methods by which it is possible. The other possibility is that we're all living in some zoo, that basically aliens are just looking down at us, watching us as we sit there. Or all the other aliens know about the Fermi paradox, that there should be aliens that are around, and they're afraid, basically. So the question is basically, it's the same as if you're in the dark woods and nothing else around you, I've never been there before. Are you going to shout out and make a lot of noise and attract basically vicious predators? Or you can be quiet and try to hide and try to remain alive as long as possible. That's one possibility. Okay, so we can ask ourselves, how can we detect extraterrestrial intelligence? How can we find these things? Well, first we can find is space probes. This is very slow. The fastest space probe that we have will take 76,000 years to reach the nearest star. And it's also very expensive. Every space probe costs about $1 billion, and there are lots of stars in the galaxy. So the easy way is look for signals. They're cheap, power cost is minimal, they're fast, they travel the speed of light. But the question is, where do you look? All right. So let's talk about space probes. The first one is Voyager 1. Basically, will reach the nearest star in about 40,000 years. If it's captured, it will basically have a message from Earth, right? This is the plate that was sent there, right? But this isn't really a serious attempt. This is one star, all right? Another way is looking for signals. Usually is look for radio. So it turns out that radio is a great idea, but then it's like the FM AM dial on your car radio. What frequency should you look at? Well, it turns out there's a range of frequencies between 1420 and 1600 megahertz, which is especially quiet. It's known as the water hole, right? Beyond it's pretty noisy. Below it's pretty noisy. But right in that middle is a pretty nice signal. And hydrogen emits this frequency. So basically, if any civilization knows about astronomy, it's going to be looking in this region. So if you want to communicate with this civilization, make yourself known, this is the place to basically be listening. All right. So one search was conducted with a serial observatory, basically generates about 35 gigabytes of data per day, right? And to analyze this, they need a lot of computers. So one possibility is basically outsource it to volunteers. So that's what SETI Home does, uses computers' idle time to basically process radio data. And they found some promising signals, but it's very all inclusive at this point. Okay, but one thing we know about our civilization is that as we get more mature, we tend to use more information technology, and we need to basically send signals faster, right? So for instance, we don't communicate using radios anymore. We do cell phones and Wi-Fi, but that's much higher frequency than the water hole. Okay, to carry most of our signals on Earth, we actually use lasers like fiber optics, right? But alien civilizations may use lasers directly to communicate. We can actually, in fact, do that on Earth, right? And so basically, the reason why is visible light can hold a lot more information than radio. And so there are a few searches on the way, basically looking for laser signals in the sky. It's optical SETI, right? So to piggyback on other observations.
Oh.
The only question, how do you communicate? So one thing is, how do you communicate with ET?
Phone? He said phone? He said phone? a phone.
Home.
You're right. That's E.T.'s home.
E.T. Home phone.
E.T. phone home. E.T. phone home. E.T. phone home. He wants to call.
So how do you actually talk to them? E.T. knew English, but English is, unless you're in Star Trek, English is not a universal language. So you have to use a universal language, and that language is actually mathematics. So in 1974, Arisu actually did send a message to a distant galaxy cluster M13, which consists of 1679 bits. Now you might wonder what's special 1679. Well, if you knew about mathematics, you would deduce at some point that it's basically the multiple of two prime numbers, 73 times 23, right? And if you arrange this in the pattern 73 to 23, you get a picture out. And there's the picture, okay? I don't remember all the pictures here. So this is DNA. This is the humans, all right? This is the sun. It basically says that we're the third planet from the sun. This is the Arecibo telescope, which actually sent the signal. And that's it.